Alright, good evening students. Welcome to lecture 2 of topic 3 of unit 3, wave interactions. This video is going to be going through the main ideas of chapters 14.3 and 14.4 of the, book 1. Please have a read of that before class. Here are our learning intentions and the success criteria. Have a read and complete the KS table down here on the bottom right. Thanks. Okay, now, so we see here, I want you to be able to explain how waves behave at the boundaries of media, and I want you to be able to apply wave superposition to demonstrate a standing wave. So there are 3 criteria we're looking at here. You've got to be able to define a couple of terms. There's a couple of others that go with this criteria, but we'll get to those later on in the unit. Apply superposition to determine the result of wave interference. And explain how superposition leads to forming standing waves. So through our knowledge, well, we need to know first off, what is superposition? Oh, that's weird, the animations have gone out of order. What is interference? How do waves behave at boundaries? And what is a standing wave? Now, in terms of the skills, well, I'd like you to be able to apply superposition to things, so that way we can do this sort of calculation and explanation. So let's start with mediums. In the world around us, waves go through a lot of different mediums. And what I mean by that are the substances. Light goes from the vacuum of space into our upper atmosphere. It goes from the air through the glass in the window and then back to air again. Sound can travel through walls, the foam covering of your headphones before going through the air to the eardrum and then moving through the flesh and the fluids inside your ear. All these substances that waves move through are called mediums. Okay? Whenever a wave moves between mediums, some change to the wave properties we discussed in our last video will happen. Now, we're going to focus predominantly in mechanical waves here, but this is still true for electromagnetic waves as well. Light will change, for example, its velocity as it goes from space to air and then to into like gems, for example. Diamond, it's about half the speed. So actually maybe let's just take this and get rid of this word. Substance that a wave moves through, any wave. Okay, well, as I just mentioned, for light and its speed, the speed of a wave depends on what the medium is made of. Okay, now, there's a great table in your text that has a few different types of waves. It's got earthquakes down underneath it as well, or tectonic waves. And you can see here that different substances, different gases, the speed is quite different. Speed of sound in air is about 331, depending on the temperature. Hydrogen, pure water, salt water, glass, like the Pyrex glass that we use for our beakers and our test tubes. And you can see here, as we get through gases into liquids into solids, the speed is increasing. Light, with the vacuum, it's very, very high. With air, it's very, very high. But glass, it starts to get a little bit lower, close to a third that of the speed of light in air. If we go down to diamond, I believe it's about 1.5 times 10 to the 8. It slows it down by about half. Still pretty fast, but it's reducing things by quite a lot. Now, when 2 mediums meet, that's called a boundary. Okay, so that's an important word to keep in mind. So let's start talking about what happens at boundaries. Whenever a wave interacts with a boundary, reflection always happens. Okay. Sometimes the reflection might be very small, nearly nothing. Light hits the window. You don't really see the window too much, especially if the glass is clean, so there's very little reflection happening there, but a little bit does. Okay? There's stuff on the glass, it's dirty, or a wall is very opaque, lots of reflection happening. Okay? But there's always a little bit of reflection. Now, if you think back to the practical, or the simulation that hopefully you've had to play around with, when you have a wave interacting with a fixed boundary, you've got a string or a spring anchored to something, then the reflection gets inverted. It shifts out of phase. Okay, well, when a wave hits a fixed boundary, there is a phase change. Okay, so here, wave coming in, we can see the pulse is up the top, hits the wall, comes backwards, upside down. Now, all of you, the year 11s did this in year 10, and the year 12s did this last year in year 11, you all did Newton's third law last year. If you think about what Newton's third law is, and you think about the idea that this is trying to force the boundary wall up, you can probably figure out why it inverts, and I'll leave you to work that out. In contrast, when a wave reaches a free end, like this, it doesn't invert. The wave flicks the ring up, the ring comes back down, the wave goes back in the same direction. Okay? There's a little bit of loss of the wave into the air around it, but otherwise the wave just gets there, goes up and down, and then comes back. When we deal with fixed blocks and free air, they're pretty extreme cases for mechanical waves and ropes and slinkies. If the boundaries are very similar in density, like two different springs, reflection still happens, but transmission also happens. So if a wave goes from a light spring to a heavy spring, so here we have a drawing, we can see the light spring is quite thin compared to the heavy spring. Okay, it gets to this boundary, what do you think might happen? Well, what we see is this. Some of the energy gets reflected back, but it's upside down. Well, some of the wave continues on, but you notice here that it's quite a bit smaller. Right? This is because the energy gets split, depending on the proportions of the density, but also because this is a bit heavier. The same, even if it was the same amount of energy, even if all the energy moved onto it, it still wouldn't move as much because it's heavier. There's more mass to it. Okay? Now, if we go the other way, if we reverse it, and we have a heavy wave coming into a light spring, what might happen here? Well, you may have sort of clued together here that we're still going to have some transmission, and like we saw up here, the transmission will still be in phase, but the reflection will also be in phase. Okay, it doesn't get inverted, it doesn't get turned upside down. Again, because some energy is passed on and some comes back, the size is still less. Okay. Now there's a table in the text I've put down here that summarizes this. If we have a fixed end, the reflected is out of phase. If it's a free end, the reflected is in phase, but there's no transmitted. I'll talk about that in a second. Light to heavy, out, the transmitted is in phase. Heavy to light, in, transmitted is in phase. So that's a reasonable table to think about, but I actually think a little bit the deeper cause is lost here, because I want to talk about these blank spots. I want you to think about a fixed block. Some energy must get lost into that wall. Otherwise you'd have a 100% efficient wave, and there is no wave that does that. So some of that energy is transmitted into that wall, and the wave continues into that wall, just not very far. The particles are fixed. Okay? There's a little tug on it up and down, but the wave doesn't propagate, doesn't continue, and so most of it just reflects back. Okay? Newton's third law. With a free end, the wave does move into the air. It's just that air has to move at a particular range of frequencies for you to hear it a sound. And a really good example of this is to think about a whip. The tip of the whip, if you flick a wave pulse down a whip, that tip, you can hear a crack, you can hear a sound. Okay? That means energy, some work had to be transferred from this moving whip into the air around it to create a sound pulse that you could hear. Okay? Sound is energy. We've established that. We learned about that in grade 8, and we've talked about it in our very start of this unit. We started talking about energy moved into heat. So there must be some movement of energy from the wave. So in my view, there's actually a more general process happening here, and it's all about when energy in a wave goes from one medium to another. If the medium is denser, the reflection is out of phase. How much goes on depends on the density. If the medium is less dense, the reflection is in phase. And you can see here, light to heavy, well, light to really damn heavy, out of phase. Okay? Heavy to light, heavy to really super light, in phase. So I take this and I think, well, no, it's just these two things happening. If the second medium is more dense, the reflection comes back out of phase. If the second medium is less dense, the reflection is in phase. It's just that fixed or free ends happen to be super extreme versions of more or less dense materials. Alright? And that lets you figure out how much is transmitted on. Okay? The more that the density is, the less energy that gets transmitted on when you go from a light to a heavy. If this was a very, very low density, then there'd be practically no energy transmitted onto it, because it just wouldn't take the amount of energy, or the amount of energy needed to move it is very little compared to the amount of energy to move that. Alright, now that's one-dimensional reflection, where something is coming along a line, gets to a point and either goes backwards or goes forwards. So that's one-dimensional reflection. I want to talk about 2D reflection very briefly now, but we are going to come back to it in Unit 4 when we talk about light. So there's one thing you need to learn right now about reflection. Angle of incidence equals angle of reflection. We learned about it in grade 9, but we're re-establishing it now. This is often given by a formula like this. Theta I equals theta R, and this is what it looks like. Theta I is this angle here from the normal, the perpendicular line out of the wall. Same with theta R. It's not these ones, even though they are equal, they are only equal because it's flat. If this was curved, wouldn't be, the bits on this side would not necessarily be equal. But these two, these internal angles off the normal, will always be equal. This relationship is not written in your formula booklet. You're expected to know it. Okay? That's it, what we need for 2D reflection at this point. Keep this in mind when we get to Unit 4 in late Term 2, early Term 3, and we start looking at quantum mechanics, and I ask you this, I expect you to remember it. So let's talk about the last part of our lab, interference. If you've ever seen two different spotlights shine on a location and produce a new colour, you've seen interference. Okay. Here's an example. Here's three different spotlights. I couldn't find one with two, but here's a blue spotlight, a red spotlight, and a green spotlight, and you can see where they cross, they're producing a new colour. That's interference. The waves are working together, and you can also see that, you know, this bit here is pretty dim, but this bit in the middle is quite bright. Okay? And brightness is a nice, really easy example. If you want to test this out for yourself, all you need is some cellophane and some phone torches, or any torches at all, but most of you would have a phone, so a phone torch is pretty easy to use. But yeah, you just need two different types of cellophane colours. Use blue and red, shine them together and make purple, or use red and green and shine them together and make yellow, or use, red and yellow together won't do much because yellow is just, part of green and red, so make a sort of reddish yellow, which, I guess is orange. But give it a go with those. But brightness, that's another good way of thinking about it. Here we have a diagram or an image with two spotlights. And the spotlights here, you can see where they meet at the bottom, it's making quite a bright circle. But the spotlight continues, and you can see that this wave is dim, gets very bright here in the middle, and then gets dim again. Dim, bright, dim. Or across the floor, where the two waves meet, this area here is quite bright. But where the waves are not hitting the same spot, it is quite dim instead. And this tells us something really important about waves. When waves meet and interfere, they keep travelling past each other afterwards. If two waves cancel, like noise-cancelling headphones, the sound doesn't get destroyed, it's just cancelled in that one area. Okay? Now, interference will come in two types, and you definitely need to know these names. Oops, I managed to make them vanish, I forgot about that. Come in two different ways, so please write these ones down. Constructive interference and destructive interference. So we need to know those language. Alright? Now, let's have a look. Here's two examples of waves meeting. The first one, they are meeting out of phase. You see here the two pulses come together, they meet, and suddenly they're gone, but then afterwards they continue passing. Here's two waves in phase, meeting, they get bigger, and then they continue passing. Okay. There's no interaction between the two waves. What's happening instead is that both of them are contributing, okay, to the change in the medium at that point. Okay, but the waves don't interfere with each other. Constructive interference, you see, is making a supercrest, and what's really important to note there is that the width isn't actually changing. Just because the wave is taller doesn't mean it's making it bigger. It's only giving it a bigger amplitude. And this is called superposition. Superposition, as I've got down here, is the idea that when two waves overlap, you can add the amplitude at each position to get the result. And this is both for constructive and deconstructive interference. Let's have a look at an example of this. So, my drawing is probably not going to be as good as Walding's on this, but let's give her a shot. We're after construct the wave pattern produced when each of the two pulses progresses 5 squares and they overlap. So if we think about this, that'll go forward. They're currently 1, 2, 3, 4 squares away from each other. So this point here will go forward 5 squares and end up about here, and this point will go forward 5 squares and end up about here. But the waves are 1, 2, 3, 4, 5, 6 in length. Okay, so A is going to go from here to here, and then B would go from also here to here. So realistically, and that's what all these sort of questions are going to ask you about. Sometimes some more complicated ones might ask you to draw multiple stages for it, but this one's just asking, basically draw them overlapping each other. And what I'm going to do is I'm going to draw both waves. Not great, but I'm going to draw both waves. I'm going to draw my equilibrium point, or my equilibrium line, and now I'm going to draw my two waves. It starts off steep, goes down to there, starts off quite steep, goes down to there. So I'm just going to pick a couple of points because it doesn't really matter too much what I'm doing here. This one here is 1, 2, 3, 4 points high, and that is 2 from the end. So since that is going to be 2 from the end, that would be back here, and we can see that that would line up with that 4. This is why doing this on grid paper can be a lot easier. So all I've done here is I've gone, well, these are the same width. So if this is 2 in from here, I want 2 in from the end there. Okay. This has a height of -4, this has a height here of +2. Well, what's -4 plus 2? It's -2. And so our, let's see, do I have a different colour? Let's do our resultant in blue. So our result here should be at this point, it'd be about -2. I'm just going to put a scale up there, -2. And because it's symmetrical, it's the same shape, we know that this one must be about +2. Okay. Now, let's find our middle point here. So 1, 2, 3. Our middle point here is 1, 2, 3, about -3 down. And here, 1, 2, 3. Our midpoint here is about +3 up. Well, that's good. What's -3 plus 3? Well, that's 0. So that must mean in the middle here, it cancels each other. Now, I don't need actually to do any more math than this. Okay, and it's a sort of a little trick. It's not really explained too well in the text, but the way I like to tackle these is I find these points where things change, and then I go, well, I don't need to do all the math for the internal points. All I need to know is that they're both straight. So that means the resultant line, when I add them together, should also be straight. Okay? And so from here, I'm just going to draw, well, it goes straight to there, it goes straight down to there, told you my drawing's not that great, and it goes straight up to there. And so our resultant wave gets a little bit smaller here, a little bit smaller here, and cancelled in the middle. Okay? And it won't matter what you have to superimpose. There are some questions of this in the revision, in the end of chapter questions, which I really recommend you try, even if I haven't actually asked you to do it, just because it's good practice with the drawing. But that's an easy way to think about how to do superpositions. Find a couple of critical points and then just extrapolate the bit in between. Okay. So the last part of this is standing waves. So if we have two continuous waves, okay, so not just a wave pulse, but two continuous waves, a set of pulses, have the same amplitude, and same amplitude is not even really needed. It helps. At least it helps in this case what we're going to start with to make easy stuff, but you can do it even without the same amplitude. It just makes the result more complicated. And frequency, but again, it doesn't have to be the same frequency, but it does have to be specific frequencies. Then you get a standing wave, and the only way to really show this is to show you. So here's an animation, and we'll wait for it to loop back through, but here we have a red phase, a blue wave going this direction and a red wave going this direction, and you can see here now that it's looped, and when they get together and they meet, we see, oh, it gets bigger, small, and you see these bits here start to get bigger and bigger. You notice that our resultant wave doesn't look like it's moving left or right, it's just going up and down, but this black wave is made of our red wave travelling left and our blue wave travelling right. I'm going to follow along here. I'll just call them out as I get through. So nothing, 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 nothing. Constructive, D, con, D, con, D, con, and then passes off. Wherever I said constructive, the waves are in phase together. They were both amplifying. When I said it was deconstructive, that means that the wave is out of phase at that point, and so that it ends up cancelling it. Okay? Another example, and this is one you can try with a simulation, is what happens if we will let it loop back around, but what happens if we have a wave approaching a fixed point? And this is really important for music. So we can see the wave comes in, and if we remember our bits, we can predict which way the reflection will go. Okay. And because it's now reflecting a waveform back with the same amplitude and the same velocity and the same frequency, we end up creating again another standing wave. I'll let it loop back around and watch it again. It's quite hypnotic really, isn't it? Alright, so our wave is coming in, and it gets to the wall, and the wall starts to invert it. So now almost get it just right where it needs to be. Okay, and so that wave is in phase and ends up creating positions where we see lots of movement and positions where we don't see much movement. This is called a standing wave. So a standing wave is a wave with a stationary vibration pattern caused by superposition of waves with particular frequencies, and it creates two special points: antinodes and nodes. In fact, I will just mark them to clear it. Antinodes and nodes. Alright. Now, antinode is an area of, or a region of high amplitude, and regions of no amplitude are called nodes. Now, the problem is the word anti often makes people think of nothingness, or of something being removed, which isn't the case here. It's the opposite. So the way I remember, the trick I use, the word node sounds like no for no movement. So a node has no movement. An antinode is the opposite of a node, is the opposite of no movement. The opposite of no movement is lots of movement. Now this is going to be really important for when we do sound, so you've really got to wrap your head around the idea of a standing wave. And so if we're going to explain this, the standing wave is happening because this point here is a superposition of two waves in phase, and they're always, the points crossing here are always in phase with each other. Okay? This point here is a crossing over of 2 points always out of phase. One's up here, one's down here, they cancel. One might be here, one might be here, they cancel. They're always cancelling. Okay? So we want to be able to explain that, because that's probably the hardest part of this topic, just being able to explain how superposition leads to a standing wave. Alright, oops. So, in our lesson we've gone through the following. We've looked at how waves reflect and transmit at the boundaries of two different medium. We've looked at how waves superpose over each other in order to cause constructive or destructive interference. And then we've seen how interference can lead to the creation of standing waves. Now, for your entrance slip to class, a bit of a weird one, for chapters 14.3, I'd like you to do questions 5 to 10. And for chapter 14.4, please do questions 1 to 6, and copy your answers into the 3.3.2 space on eLearn. You can do some of the early ones, but I think that they're mostly just going to be, oh yeah, I go back here and I redefine, I just copy down a definition. So let's skip some of the really trivial ones for that one and try something with a bit more meat behind it. Thanks for listening, guys. Have a great evening, and I'll see you soon. Bye.